Hi everyone, we're Team 1097, representing Shanghai Welfare and Language Academy. I'm Jiaxuan Chen.
I'm Jinchen Liu.
I'm Sinian.
We chose problem B, an AI robots. We're going to perform an analysis of artificial intelligence model collapse by differential equation modeling.
A news report of AIP 2024 says that Jason Sadowski named the decay of AI as Hasbrook AI. Recent study shows AI programs go through a collapse when repeatedly fed their own data. It's hard to avoid AI-generated content when scraping training data from the internet. According to Paradis et al. 2025, in November 2024, the quantity of AI-generated articles being published on the website surpassed human-written articles. According to Shumailov et al. 2024, model collapse is the degenerative process affecting generations of learned generative models, in which the data they generate end up polluting the training set of the next generation. The below figure shows model collapse, which is an AI model recursively fed by its data, which is generated by itself. Intuitively speaking, the model collapse error can be mainly in three sources. 1. Statistical approximation error. 2. Function approximation error. 3. Function expressivity error.
In our solution to the problem, we include consideration from multiple perspectives, including the interaction of multiple AI models and human-written content in recursive chaining, the long-term dynamics of the impact on the model-generated content, the trend of quality change of the model-generated content, and the effect of output of multiple models in mitigating the degeneration process. First, we're going to develop a theoretical model directly from intuition on the change of the overall model-generated content quality, and then we're going to derive a more analytical model derived by probabilistic analysis to assess the change of the probability distribution of the generated data. To simplify our model, we make several assumptions. 1. Models and human generate content over continuous and infinite time with constant rates. 2. The initial training data of models are infinite and human-written. 3. The human-written contents are random variables with normal distribution. Note that this follows from the central limit theorem, which states that if random variables are independent, identically distributed random variables, then their sample mean, when the number of such variables goes to infinity, the sample mean goes to a normal distribution. 4. The data from each model in human have equal proportion in recursive training data. So first, we're gonna build a theoretically intuitive model to show the big picture. We evaluate the quality of the content with respect to human. Suppose h sub I of t in range 0 to 1 is the human likeliness of the content generated by model I at time t for all I in range 1 to k, where k is the number of models. By definition, the human likeliness of human content is 1. By assumption, the weight of each model in human contents should be equal interchange. Then we derive the system of ODEs, where the first term is the interaction term with the sources of the training data, and the second term is the error generated in the training process. So the system of ordinary differential equations, its logic is just basically taking the average of the difference between the human likeliness and then claim that the rate of change is gonna some kind of like proportional to the average of the difference of the model quality with other models, and then we add the error term to the rate of change. And then we use MATLAB to try to solve the system and found that the closed-form solutions are arbitrarily long. So we try to derive a numerical solution by generating evenly spaced epsilon of I, which are the model errors, in range 0 to 1, and then plot the solutions of each h sub I of t over t for k equals 100. And we know that these quality errors, they don't surpass each other, and they degenerate exponentially. They first dramatically decrease, and in long term, they finally reach an equilibrium. For simplicity, we set epsilon sub I to be 0.5 for all I, and then use MATLAB to approximate the average degeneration rate over t. And plotting it in MATLAB, we found out that the average rate of degeneration is actually accelerated with an exponential decay. When we first increase the number of AI models, first the rate of degeneration grows faster, dramatically, and then it'll kind of slow down and finally reach an equilibrium. But it's always monotonically increasing the rate. And in the graph, it's shown as monotonic decreasing since we took the negative. So it is the opposite to what's been hypothesized in the problem. It does not mitigate the degeneration process. It's accelerated. And then we're going to introduce the Gaussian model, which is the normal distribution. As Suresh included in his paper in 2024, possible probability distribution for the data in model collapse research includes Bernoulli, Poisson, and Gaussian. And by our assumption here is just suppose the initial data distribution is Gaussian. And now we're gonna consider our recursive training process more formally to derive a model for the probability distribution of the output data. So based on the recursive Gaussian model of single AI model, we generalize to multiple models in our research. For K models, defines the recursive training process as the set of ordered pairs M sub ij, capital sigma sub ij, for the derived normal distribution of model J at the ith generation. And then we initialize M sub 0j to be mu sub 0 and capital sigma sub 0j to be small sigma sub 0 for all j in range 1 to k, such that the human-generated content has distribution normal with mean mu sub 0 and variance small sigma sub 0 squared. And then supposing the case recursion, we take n samples from each model, as well as n sample from human, where each sample is x sub ijk, with k varying. In the ith round, for those from the jth AI model, the machine learning estimate of mu is just taking the sample mean. According to the probability distribution of the sample mean, we know that the mean doesn't change and the variance is divided by the size of the sample mean, which is n. And then for simplicity, assume that the expectation of the learning error rate is 0. Then we can estimate the recursive learning process by sampling from each model and also the human, including the K models and human, and then take the mean, which is that we take the model output and human output together and we add it, and then we take the average, which means we divide by 1 plus k. And then what we can derive is that the variance is also divided by 1 plus k squared. So it's clear that when the number of recursion goes to infinity, it's going to be 0, since it's divided by 1 plus k squared by an infinite number of time. As shown in the figure, which is an experiment of Zurich at 2024 in his paper, when the model generation goes further and further, all of the variance goes to 0, since the tail of the distribution shrinks over time, losing information. So the 0 variance is its asymptotic line.
There's still limitations in our models. Due to the limitation of mathematical device, we were unable to accurately simulate the whole machine learning model with advanced approaches such as Hilbert space, Wasserstein distance, etc. We simplify the model so that it can be solved with regular approach. After all, our model is theoretically reasonable on its logic. We have not done experiments on real machine learning models to verify our results, since training multiple large language models from the beginning has a large cost. We didn't analyze the different error rates of different specific types of machine learning models due to our limited knowledge in the specialized area of machine learning. We assumed the distribution to be normal, but the actual circumstance is more complex, possibly being a mixed distribution. When multiple AI models interact, they degenerate over time in their quality and variation of newly generated content. In long-term, variation of content will disappear with zero variety, and the quality will in turn decay and then converge to an equilibrium. The quality of AI model results decline dramatically until reaching an equilibrium, since it is an exponential decay. Different outputs from different models will not mitigate the impact of AI model collapse, but instead accelerate that.
These are our bibliography. Thank you for listening to our presentation.